So we are going to start with this after lunch part. So we will use a bunch of notebooks. So the notebooks, all of them are ready here in this repo that we have for these 2 days. Remember that there is a direct link from the repo of the Probabilistic school to this repo. And then, we are going to speak about different notebooks, starting with these notebooks about Bayesian neural network. So it's going to be just, in case you want to open it and have it there, so you can just have it here, but also the rest of the notebooks. And remember, we always provide the students version, and the solution version is going to be uploaded. Actually, you already have the solution version for the previous notebooks as well, okay? Yeah. So, this morning, we introduced you to the basic ideas of variational inference. So variational inference as a way to do Bayesian modeling, a Bayesian inference, and in a way that scales, to models with a large number of parameters and in data sets with a large number of samples. Even though the kind of models that we have been using this morning has been models that are simpler, in the sense like they can essentially model the relationship between random variables using a kind of linear relationship between random variables. Perfect? So that was the reason, because in order to derive these variational updating equations, this model has to be within a specific model family, which is called the conjugate exponential family. Even though, this conjugate exponential family really includes a lot of different models like linear regression, latent drill-edge allocation. This is a very nice model for text modeling. It was very popular. But of course, we nowadays have models that are more complex than that, because the needs now are different. So we are aiming to have models that are able to model non-linear relationship among random variables, more specifically. So we aim to have models that are as powerful, as flexible, like neural networks. So, and then I'm going to just to illustrate a bit the kind of thinking, or the kind of ideas that, the kind of needs that we need to have in order to do Bayesian inference or models that can represent non-linear relationship between random variables. And then after that, Helge will give you, which are like the main methodologies in order to perform Bayesian inference, more precisely variational inference over these more complex probabilistic models. So in this figure, I want just to illustrate that we have a random variable x, another random variable y, where there is a non-linear relationships. And then we know that neural networks are quite good in capturing non-linear relationships between random variables. Here I just have code in PyTorch, plain code in PyTorch, when we just define a simple multilayer perceptron. And here we define the weights, the bias of the inner layer, and the weights and the bias of the last layer. And then what we do here is we just using the mean square error, we just trying to find which is the set of weights that best fit the data. And when we plot it, what we have is something like that. This is the data, and this red curve is just the function defined by the set of weights that I have found, minimizing the mean square error. But we have told you before on several occasions, this is one of the possible models that can really fit the data. So as you can see here is like one can imagine that another line, that does something a bit different, could also be a good explanation, for fitting the data. And this is something like doing Bayesian inference. It's like considering a posterior distribution over the parameters of my model. That really means consider a distribution over alternative neural networks is a way to capture this uncertainty and make better reasoning. So in that sense, we are going to use Pyro. The idea is like we can use Pyro, and then when we define the multilayer perceptron, instead of defining the multilayer perceptron, sorry for going back, find the parameters, what I'm going to do is just define the weights of the multilayer perceptron as random variables that are normally distributed, okay? And then I'm going to define the nonlinear activation function, and then I'm going to define the observations, again, as a set of random variables, okay? I'm going to define the model in a probabilistic way, where now the parameters are going to be treated as random variables, and my problem is computing the distribution over these parameters condition over my training data set. Yeah? And then I can do this, again, invoking stochastic variational inference. But now the kind of stochastic variational inference that we are going to use is black box variational inference, which is going to be the topic of this after lunch session. The question is that when I run the stochastic variational inference, I get trying to optimize the elbow. So I'm going to define a mean field variational assumption, okay, a distribution Q, and then I'm going to find the distribution Q which is closer in terms of the chiral divergence to the true posterior, and then I'm going to do that by maximizing the elbow function. And this is something that I will be able to do using a stochastic variational inference and the techniques that we are going to see after that. So the elbow is maximized until some point, you know, that you can give, of course, more epochs and get better, but it was enough to illustrate the purpose. And the main point now is like, instead of having a single line, okay, instead of having a single neural network, I'm going to have a bunch of neural networks because I have a distribution over the weights of my neural network, so I can sample. You know, from this posterior distribution, every time I sample, I get a configuration of my weights that define an alternative neural network that defines an alternative function trying to fit the data, okay? And at the end, what they have is the possibility to capture the uncertainty, okay? So these are kind of alternative explanations, okay? Instead of having a single explanation, in a single model, I have a bunch of models which are defined by the variational approximation to the true Bayesian posterior. Perfect? So that's the kind of thing that we are going to see, okay, right now. So how we can do that, okay? How can we implement variational inference in the context of these complex models? Because what we've seen before lunch doesn't really apply here, okay? So the next thing that then you have to think about that is like the variational inference is so powerful that they start to be applicable to much more really complex models, okay? And during the rest of the week, you will see, you know, much more interesting examples, okay, or how that can be, you know, applied to real big neural networks, or also like for generating images, diffusion models, and so on. So the core ideas are going to be mostly the same. Perfect? So any questions so far? Okay. So here you also have a kind of optional exercise in order when you can also model the variance in terms of like Bayesian approach and so on. You have the notebook, so, you know, feel free to have a look at the notebook. I mean, if at some point you are interested in the details. Perfect? So, yeah. So, no questions?
Okay, so we will start by stochastic gradient descent. I know it's annoying because you all know how that works already, but there is one point I think we really have to make very clear. And we discussed and agreed that you should be punished by watching me go through these slides, so that's what we do. So our big plan now is to optimize elbow using gradient descent instead of using the CAVI approach that we had before lunch. And as Andrés showed you, this gives us the opportunity to mix in other stuff than standard distributions and standard linear relationships between variables. So it's going to open up the door for more powerful models. We just need to find out how to do this. And in practice, that means finding out how to calculate the gradient of the elbow. Okay, so our starting point is gradient ascent. And as we all know, this is how we do that. So we have a function f that we want to maximize. This is a function of lambda. And our algorithm is basically just to start off somewhere and then keep going in the direction of the gradient until we are happy. And hand-waving-wise, this works when f is nice and the learning rate rho is sufficiently small. So this is kind of the starting point. And one might think that this would be enough, but it's only almost enough for handling elbow. And the reason for this is we don't know how to calculate this thing here, the gradient of the elbow in analytic terms. So, there are at least two reasons why this is difficult. One is that we might not be able to load the full data set in one go. So that means that we have to do mini-batching, and therefore there is a random element towards which data points are included in each iteration, and therefore something happens there that needs to be taken care of. And the other is maybe, even though we were able to do all the data in one go, we wouldn't be able to calculate the elbow. And that's also going to be the case. So then we would like to approximate that in some clever way and then use those instead. And therefore also then this stochasticity element in the algorithm. Okay, so the crux of the whole thing now is we don't have the gradient, but what we will assume that we have is this g function here. And that is our magic approximation to the gradient. So this is a random variable. It has finite variance, and it is unbiased. So unbiased means it is correct in expectation. The expectation of g is the gradient that we are looking for. We don't know what the gradient is, but we will have an estimator that is correct in expectation. If that is the case, then we are almost good to go. We also have to tweak a little bit on the learning rates here. So the learning rate is not a constant anymore, but it's a sequence of numbers that gradually declines towards 0 in such a way that the sum diverges and the sum of squares converges. So some small technical details that we won't really care about, but the main thing here is what is in red. We will be happy and be sure that we will have a successful use of stochastic gradient descent if we can come up with an estimator of the gradient of the elbow. So that is now our task. Make sense? Yes. Good. So now we are heading into what is called black box variational inference, which is the first attempt on a most general way of doing this. And then after you will see the reparameterization trick, which is a special purpose method that is working better when it works at all. Okay, so now our plan. We want to optimize this elbow by stochastic gradient ascent. So the algorithm would be straightforward. We have the elbow here. We will just initialize somewhere. We will have a Robbins-Monroe sequence, and we will update our variational parameters following this scheme. But all of this then hinges on our ability to calculate the gradient of the elbow. And that is what we will look at. So we are now trying to reformulate the way that this can be calculated. And we will do so in ways that are not too restrictive when it comes to the models we can work with, the P distributions, and the approximations that we can work with, the Q distributions. And specifically, we will come up with some requirements for Q, and they will not be too restrictive in this setting here, in the black box variational inference. Okay. So this is the starting point. This is the elbow that we saw before lunch. This one here. And now I just added the gradient sign in front. And now the question is, how can we calculate this thing? So one immediate problem is, of course, the expectation. That would involve doing an integral over something here that looks slightly nasty, and where we multiply by q and integrate, which is certainly going to be nasty, so that's not going to work. And typically when we have integrals of this kind, where we are actually trying to find an expectation, the go-to method would be to just sample it, right? Sample some examples, generate some samples from Q, evaluate this thing here, and then do the sample average, and this is your unbiased estimator of the expectation, right? So in that sense, I'm kind of moving towards something that sounds like can work with stochastic gradient descent. I'll be able to sample my way through the expectation part and get something that is unbiased. Problem, though, is how do I then do the gradient of that again? Because I'm now taking the gradient with respect to the parameters of the distribution that generates the samples, which sounds kind of unsolvable and is also a little bit tricky. This does not invite immediate use of sampling to get the expectation and the gradient. So we need to do something that is a little bit more clever. And here there are some mathematical details that we are sparing you from. So what we're trying to do now is to find a way to reformulate this thing here so that the gradient is put inside the expectation operator. And using these three rules, so the product rule, the log trick, and here that the score function has expectation 0 is three things that will then help us. If we just try to write out what this is, we end up here using these three tricks. We're sparing you the details. You can probably do it yourself if you are bothered to do so. Just ending up here, and this is what is called the score function gradient. So now we know the gradient of the elbow, or at least I know, and you trust me, I hope, the gradient of the elbow can be calculated in this way. And now we have the expectation operator outside everything else, meaning I can have an unbiased estimator of the expectation using sampling, meaning I am ready to do stochastic gradient descent. So that was kind of the steps needed for coming up with the score function gradient. So let's look at this beast a little bit more and see where we are at. Is this something that we can work with? So first off, we have here the part where the model description comes in. And the good thing is, of course, we have still this joint distribution over parameters and data together, which is something we can calculate efficiently. We are not relying on finding the posterior or anything like that. So this is easy to handle. No requirements towards the model, except that we should be able to evaluate this joint density. So that was nice. And then comes the Q. So we will here still utilize mean field. And the reason why we do that is that we can then efficiently optimize each direction or parameter independently. Could have done more advanced stuff. We are not going to do it. Next, this part here. This is the thing called the score function. So what happens here is we need to be able to calculate the gradient of the log PDF of this Q distribution with respect to the parameters. This can either be done analytically if we choose a parametric family that we're happy with, or with autograd or whatever. So this seems solvable as well. No big constraints on the Q family when we just claim that this is something that we need to be able to do. And then finally, the expectation, and as I have alluded to already, we are going to approximate that guy using sampling. So this means that we have this strict requirement. We need to be able to sample from the Q distributions. Otherwise, we don't know how to evaluate the expectation, and then we are kind of screwed. So this is the requirement we have. We need to be able to sample from the Q, and somehow we also need to be able to calculate these score functions. And if all of this is in place, then we can actually then calculate the gradient of the elbow directly. So the setup is kind of clear. Say we are at a parameterization lambda hat, then we calculate the gradient evaluated at lambda hat by just sampling from Q. So then that gives us a set of these theta variables, right? We evaluate that with respect to that lambda hat that we have, and then this gives us the gradient, and we make the small move, and we keep going. Here you see I have made the sample average over this sample that I used to approximate the gradient. Typically this number is fairly small. The number of samples that we use is fairly small, say 10-ish, something like that. And then we rather do many iterations instead of being really, really clever at approximating each gradient. Yes? Yes, so let's do it here. So what I'm sampling are samples from theta. And theta is sampled from the Q distribution. So I'm trying to approximate this expectation here. And I do that by sampling thetas from Q and evaluating this thing inside here with these samples and averaging. So this is the sample average as a proxy for the expectation instead. So how it works is that I'm sampling here. Here I have 5 samples, all coming from the green Q curve, Q distribution. So these are contour plots, right? 2-dimensional, theta 0 here, theta 1 here. Think about the regression model again. My current estimate is Q is this green thing here. I sample from it. I get these 5 samples. I'm going to evaluate this magic thing within the parentheses and average them, and that gives me the gradients. So that's how it works. Yes, yes, and they are, because it's the one example that we actually are able to solve. Slightly embarrassing, but everything here is linear regression, I think. So that's how it is. Okay, so let's look at what we have here more in detail, focusing on that data point here maybe. So this is one of these samples that we will use to approximate the gradient. So approximate the expectation of that thing within the parentheses. So that thing is basically what is written here. So starting at this data point, the first thing we do is to evaluate the score function, which is this gradient here, evaluated at that data point. So this thing is basically asking, how should I change my Q distribution to make that sample more probable? This is what we're doing with this red vector here. So to get that point to be more probable, I need to push my Q in that direction, right? So that's why I'm getting a small vector here. This is indicating that the whole distribution should move towards the data point. If this guy gets to decide, then move everything here. So that's this part here. Then this is weighted by this thing in front, log P of theta and D divided by Q of theta. This is a number that is typically small. One thing is we sample this theta value from Q distribution and not from the P distribution. And here you can see they are different, so that means that it's typically more likely under Q than under P, the data point that we have. And also, the P thing here is the joint of theta and the data, whereas this one here is the conditional. So this number is typically way smaller than that one, meaning that this fraction is less than 1, meaning that the log is negative, meaning now that the vector, this little red guy, switches direction and grows. We're multiplying it by a number that is way smaller than 0. So we get this vector here instead. And that's the contribution from that single data point. And then we average that here over 5 samples, leading to the end result, which is this guy. So from these 5 samples, this is the approximation to the elbow gradient, moving us now in this direction here based on these 5 samples, which is kind of unfortunate because it's not the way we would like to go, but this is what happens when you have an estimator that is not exact, but is with variance larger than 0. It's somehow pointing us on average in the right direction, but each and every one is not guaranteed to do so. Does this make sense, or is it just like strange? No comments. You're my guy. Strange or sense? Good. Jesus, I didn't expect that. So let's see what happens if I'm using different samples of 5. So in this one, top left, I have the gradient going, the combined average gradient is going here. Here, in this plot, it's going up there. This plot is going like, where is it even going? There, I think. And here it's going there. So like they are all over the place, but if you average over these 4 plots again, it's kind of pointing towards where you want to go, right? So we have here a high variance issue, but on average, they are pointing us where we want to go. And this is also then describing the behavior after. We will be moving around a lot, but we will get there eventually. One obvious idea would, of course, be to increase the number of samples that is used to approximate the gradient. Here we see the effect of that. Here, starting with 3, that's the perfect one almost, so that's strange. But shit happens, and good things happen. Here, 5, here, 10, and here, 25. And of course, the key here is you would like to visit the full Q distribution when you're averaging. So the more like balanced and spread out they are, the better. And the more samples you have, of course, the better. So that's kind of the effect we see here. Okay, so here is a video again, where you can see that it's kind of dancing around a bit, but eventually getting where it is supposed to go. Not the structured or behavior that we saw from the Kavi before lunch, but more like all over the place, but zooming in and getting to where it needs to be. So this is the behavior that we expect from a stochastic algorithm, of course. And now you guys are going to play a little bit with this stuff. It's our good friend, the linear regression model, once again. And you are going to implement only a small part here. Most of this is already done. So what you will do is open this notebook called the BBVI, Black Box Variational Inference. And what happens here is starting off with generating some data and stuff, and then we are here giving you implementations of P, of the data and thetas, and of Q, so you don't have to do that calculation of the weight stuff. And we do the elbow, and we basically also do how the gradients are combined, or the samples are combined into making a gradient that is averaged over different samples. So the only part that we are asking you guys to do is to calculate this one, the score function. And you're only supposed to do it for the mean. So we need a way to calculate the score function for the means of a Gaussian. And we are giving you how it works for the standard deviations. So your only task is basically to fill in the thing for the mean. And that goes in here. And when you have done that, you are able to play around with the code and see how it works. So here in this cell here, we are like generating the stuff and seeing that it plays. So I am inviting you to do this, but maybe I should show you a little bit of the code first. So the key structure here is something called parameters, which is a Python data class where we have two labeled positions, mean and standard deviation, and these are the ones that we use for doing all the data storage, and this is the one that you are going to fill up. So when you are calculating basically the movements here, then they are in the direction of the mean and the standard deviation, and you are supposed now to do the mean. So let's see where that happens. Yes. Yes. So this happens here. Here we can see that you are getting the Q distribution in, the prior distribution in, the observation noise in, and the data. So then you are, or we are already sampling theta values of the correct size. And calculating the weight, which was the one that got us from the red vectors to the black vectors previously on that slide. And then we need the score function part. So actually the red part, the vector parts in my previous plot. Here I'm just like filling in blank zeros for the mean, whereas it should be something else that you need to calculate. Then what happens here is that we fill in the data storage slot and then send it back. So it's not much. It's like 2 lines of code needed here, but you need to have the correct lines of code, of course. So that is kind of the question now. What is the score function for the mean? Does that make sense? No? Yes? Thumbs up? Good. So then how many minutes do we have for this, Thomas? 10 or something? 15? 15, yeah. So when you run it, you will see that, or you might see that the system is complaining a bit. One problematic issue is to set the correct, or a functional learning rate. And what's happening here is that sometimes with the learning rate that we have, the variance is suddenly going below 0, which is kind of unfortunate. So then it's complaining and changing the learning rate and keep going. But it generates some warnings. So if you see warnings, then don't start. Don't lose belief in yourself. Don't lose the belief in yourself. It's how it's supposed to be, and then you'll generate some plots and see that it actually converges anyway. Okay.
Yes. So we are going to continue. Hi, everybody. So we are going to continue. Please have a seat. Okay. So far we are kind of, so we have shown you how to do variational inference without having to manually derive this coordinate dating equation based on this stochastic gradient descent, okay, using the score function. Yeah. But the problem of this, or maybe like, does it really work, this score function approach for computing the gradient of the elbow and trying to optimize the elbow, and when optimizing the elbow, finding the variational distribution that best match, okay, the true posterior? The problem of this method lies clearly here in what Helge saw before, which is about the variance. So as Helge showed you, so sometimes here took in 5 samples, okay? Sometimes we can get a nice direction, kind of nice direction, sometimes not, sometimes yes, so there is variance. So the variance means like the Monte Carlo approximation on the underlying expectation, okay? Because it's a Monte Carlo approximation of a function which is a gradient, okay? And this function it's a gradient. So it's like when your model has 3 parameters or 2 parameters like here, we can live with this variance. When your model has 10 parameters, maybe we can live with this variance, okay? But when your model has 1,000, 10 of 1,000, millions of parameters, this variance becomes so high that make the estimation of the gradient really, really poor, okay? And makes the method not really practical. In theory, the method will converge because the expectation will be there. But the problem is it may take so long that it's not really a practical method, okay? So we have a problem with the variance in the way that we are estimating the gradients. So what we are going to show you is another method, which is called the reparametrization trick, which is an alternative approach to compute the gradient of the elbow. Because once we have the gradient of the elbow, or a nice estimation of the gradient of the elbow, we can optimize the elbow function, and then we can do variational inference. So again, we have the gradient of the elbow, which is the gradient of this function. So this is the elbow, okay, and then we have to compute the gradient with respect to the variational parameter. Okay, now we want to compute the gradient of the variational parameter to optimize the variational parameter, to optimize this function, okay, across the different variational parameters. Yeah. So what we're going to do now is I'm going to make an assumption, or more precisely, of course it's an assumption, but I'm going to exploit a specific structure that is present in many of the variational families that we use in practice. And the specific assumption is like the variational distribution Q can be reparameterized as follows. Okay? So this variational distribution can be reparameterized in the following way. So when sampling from this variational distribution, I can do it in the following way. So I will have a simple density and simple distribution, and then this simple distribution, which does not depend of lambda, okay? I will sample an epsilon, okay? And then using the epsilon, there will be a function f, okay? That will map this epsilon to theta, okay? We'll map the epsilon to theta. And this mapping will depend of lambda. Perfect? So this is the kind of assumption, and this is something that we are going to exploit in order to compute this gradient. And as Helge pointed you before, the key point in order to compute this gradient is to move this gradient inside the expectation. Something that we cannot do directly because this expectation depends of Q, which depends of lambda. So we have to do something, and here we are going to exploit this property of my variational distribution for doing this. A very common example of this, widely used, is like the normal distribution. The normal distribution, when we are using the normal distribution as a variational approximation, we have this property. We can apply the reparameterization trick because the normal distribution can be reparameterized in the following way. Sampling for a normal distribution is equivalent to sampling for a standard normal distribution, 0, 1, always 0, 1, okay? And then we take mu sigma, that will be the variational parameters. Mu sigma will be the two variational parameters, so lambda will be equal to mu sigma, and then multiplying epsilon by sigma and summing lambda is equivalent, okay? So the theta that we have is equivalent of being sampled from a normal distribution with parameter mu and sigma, okay? So this is a standard trick, and we are going to exploit it in order to compute the gradient of the elbow in the following way. So the first thing that we are going to do is the following. So because sigma can be expressed as a function of epsilon and lambda, so here I have theta, okay, sorry, theta is expressed as a function of epsilon and lambda, then I'm going to replace theta by this function f of epsilon and lambda. Perfect? And now the expectation, instead of being with respect to Q directly, is going to be with respect to this phi, simple density. Perfect? So I can do this because of this property of this variational distribution. Perfect? So once I've done this, there is a very nice thing, which is like now the expectation depends on phi, not on Q. Now the expectation depends on phi, and this phi distribution does not depend on lambda. So I can just move the gradient inside. Okay? That's the trick. Perfect? So once I move the gradient inside, then I have the gradient of lambda of all this stuff. And then I apply the chain rule, and then I apply in the chain rule. I can express this as a gradient with respect to theta of this function times the gradient of lambda of this other function that was the one involved in the reparameterization of my variational distribution. Perfect? And then also appears these other terms, which is the gradient with respect to lambda of the log of the variational distribution Q. Okay? But the nice thing is you go back to, slide 5, not 7, slide 5. Okay? Point 3, it turns out that this term, when you take the expectation with respect to this guy, just becomes 0, so can be discarded, and this is the expression that we have. So when Q can be expressed in that way, can be reparameterized in that way, this gradient, okay, can be expressed as an expectation over this expression over here. Yeah. The first nice thing is like, again, because the gradient is expressed as an expectation, I can approximate this expectation using Monte Carlo. Okay? So I have the same thing that I used to have in the score function. I will express my gradient as an expectation of something. And because it's expressed as an expectation of something, I can apply Monte Carlo in order to get an approximation of this expectation.
Sorry, I have a question in the previous slide.
Yeah.
I will get one point. Before, when we defined the family of distribution Q,
Yeah.
There is like theta given lambda, but theta does not depend on lambda. And now we put that functional density between theta and lambda.
Let me see. So theta is a random variable, and the density, the probability distribution over theta depends on lambda. So you have to think that in terms of a Gaussian distribution, okay? So imagine that you have a theta which has a Gaussian distribution with some given mean and some given variance, okay? So the problem is to find the mean and the variance. So these are the parameters that we need to find, okay? So given the mean and given the variance, I can sample a theta, okay? But an alternative way in order to sample theta is like I first sample an epsilon from a standard normal distribution, and then given this epsilon, okay, I multiply by theta and I sum mean, which are the variational parameters. These two guys together represent lambda. Okay, and here, of course, it's a deterministic relationship, but in reality, the whole process is a sampling process. So we are just defining, it's an alternative way to express the normal distribution. Yeah.
So implicitly, theta depends on lambda because it defines the distribution itself.
Exactly. Yeah. Yeah. Any other questions so far?
Yeah.
Yeah.
One slide back.
Yeah.
Yeah. Why is this zero again? Can you just, this slide 5.3, can you just sketch it again?
I mean, let me see. So where is maybe if I have like this one? Oh, yes. So sorry? Yes, I have one here, yes. I mean, let me see. So you have the expectation of phi of the gradient of lambda and the log of lambda of the logarithm of q of theta given lambda. Okay. Actually, yes. Actually, there is a typo here. Here it should be f of epsilon lambda. Okay. I just forgot to replace this guy. Yes, this guy should be f epsilon lambda because theta is equal to f epsilon lambda. Okay. Perfect. And then what you can do now is like you take the expectation and then we go back to Q, to theta, sample in order to Q of theta lambda, okay, and then you have the gradient of lambda of the logarithm of Q given theta lambda, okay. And then you go here and then you have the expectation of the gradient of Q theta lambda, okay, divided by Q, theta lambda, okay, and then you have here Q, theta lambda, and then these guys cancel out, okay, and then you have like mainly a constant, the gradient of a constant which is 0. Okay, perfect? This is the kind of idea. And then cancelled. Yeah. So that's the first thing. So we can compute that using Monte Carlo estimation. But the second nice thing, and this is the key to this method, okay, is like when we look at what is like inside the expectation, which has been expanded in that way, it appears something which is very important, which is the gradient of the log likelihood, okay, of the model. So you sample a model, theta, okay? Imagine that you sample the parameters of a neural network. And then here you have the log probability that this neural network, these parameters of the neural network, assigned to the data, D. Okay? Also appears here the prior because it's the join probability. Perfect? And then inside that, we compute the gradient. Okay? And then we get the gradient. We get information about the gradient. We get information about how I can optimize this log probability. Perfect? And also appears these ones and also this one. But this is the key. Yeah. The nice is like this gradient estimator directly used the gradients of the model, something that didn't happen in the score function, okay? But that comes at a price. And the price is like the log probability of the data for the model has to be differentiable with respect to theta, not applicable to discrete variables, for example, Okay, and at the same time, also Q needs to be differentiable and reparameterizable. So it's more restrictive, but in reality works better. Well, let me see. The problem of being reparameterizable, the variational family, is not really a big problem nowadays. There is a wide range of variational distribution that can be reparameterized. People have figured out ways to reparameterize it. Okay? I mean, this is a kind of, not very recent, but it's a kind of nice survey that gives you, a lot of reference in this sense. And let me try to explain now why this way to estimate the gradient, even though we are applying Monte Carlo, we are much better, okay? And the key point is the following. So if before we have sometimes the gradient was not really pointing directly toward the posterior, okay? Right now, what is going to happen with the reparameterization trick is all the samples, when you use 5 samples, 5 samples here, okay, in most of the times, the samples, the gradient of the different samples are going to point towards high-density regions of the posterior, okay? And this is something we can see here for the linear regression model that we were playing with before. Okay? So for each of the samples, all of them are really pointing to where the posterior is. But for the score gradient, there was this one, yes, but others not really pointing. Okay? So maybe you are lucky in one same step, or in the score function, all of them are really pointing in the right direction. But in reality, there is a lot of variance, something that doesn't really happen with reparameterization gradient, to the extent that people usually implement it using just one Monte Carlo sample. Okay? To estimate the gradient. Just with one Monte Carlo sample, you get not a lot of variance to make it a practical algorithm that really gives you convergence. Perfect? Yeah? So any other questions so far?
Can we go back to the table with the columns?
Yeah.
And what are those other columns?
Let me see. So the idea here is so what happens if your variational distribution is an exponential? Perfect? Instead of a Gaussian. So the density of the exponential distribution is like that. Can we reparameterize it? Can we express it, let me see, in that way? Okay? And this is what is described here. So you can just sample an epsilon for a uniform between 0 and 1, okay? And then you apply this linear transformation, and then you get your exponential, okay? And the same happens for, different ones. I think, for example, this is a nice old blog, but appears. And the nice thing is, actually, these kind of tricks are implemented. Pyro implements many of these tricks, okay? In the distribution function, actually, you don't have sometimes even to really care about that, okay? But the idea is, how can I express this kind of densities in a way which is sampling from a distribution, for a base distribution, simple distribution, applying a linear transformation, and get back a sample from one of these densities that can be used within your variational approximation. Yeah?
Is there a good intuition behind it? Because, I still don't see why it's getting so much better. I could follow the derivation, but
yeah. Let me see. So the key point is this one. So we are using here directly the gradients, okay, of the model. Perfect. So it's when I sample a model, okay, this term over here is going to tell me where I have to move my parameters to better fit the data. And it's going to give me information for this specific parameter, how can it better fit the data. So the gradient appears here, okay? So I get information about how to improve the log likelihood of my data for this specific model. If we go way back to the score function, then we have to go back here. The log probability of the model other appear here weighting the gradient with respect to the variational distribution. So this score function doesn't have any information about the gradient. So how I can move my parameters in order to better fit the data. Only give me the way that assigns to this other gradient that is associated to the variational posterior. Yeah. here I have direct information of how can I move my parameters, okay, in which direction I can move them in order to better fit the data. Yeah. I mean, it's like this guy alone really reflects what is usually happening when you are not applying Bayesian, when you are applying a Bayesian approach. You just follow this guy. I mean, stochastic gradient descent just follows this guy. Actually, because here is encoded also like the prior, which starts to be like the regularization term, okay? So now it's like I'm considering multiple samples, I'm moving across the gradient on average, okay? And I also take into account the contribution of the variational posterior and so on. But the key point is like I'm exploiting directly information about the gradient of my model. Yeah.
This is not anymore black box.
Yes, it is black box variational inference. I mean, let me see. So, I mean, when we refer by black box variational inference, it's like we are not really exploiting, okay, specific assumptions about which is the likelihood of the. I mean, let me see. No, I'm going to be more. No. I'm going to try to explain better. Okay. So a standard variational inference, in order to optimize the elbow distribution, what we see before lunch, okay, we need that the likelihood model, that the probabilistic model that we are using has to belong to some specific family, okay? More specifically, something which is called the conjugate exponential family. So it means that if the likelihood is a normal distribution, then the prior has to be a normal distribution. If the likelihood is an inverse gamma, the prior has to be a gamma. If the likelihood is a categorical distribution, the prior has to be a Dirichlet distribution. Perfect, okay? Then once you are within this restricted family of models, you can derive these updating equations, okay? And then you have closed form updating equations. You don't need to resort to Monte Carlo methods to compute the gradient, okay? You just have closed form updating equations that tell you how to maximize the elbow. Perfect? In black box, we cannot compute this gradient in closed form. So black box means that the gradient has to be estimated, okay? Usually using Monte Carlo methods. Perfect? So the kind of assumption that I have here is much, much more mild, because I'm just assuming that I can compute the gradient with respect to the parameters of my model. Perfect? Like, a neural network is not possible to frame it within this conjugate exponential family. Okay? It's completely impossible to derive the closed form updating equation, but I can compute the gradient. Okay? Actually, there are automatic packages that compute the gradient for me. Okay? And this is one of the main advantages. Even though the score method, the score function method that we saw before is a bit more general, but because it don't even require to be differentiable. So applies, for example, to models that has discrete variables. Yeah?
Is the reparameterization trick extendable to if you take a mixture of Gaussians?
The reparameterization trick is extendable if you take a mixture of Gaussians. I mean, let me see. So if you have a mixture of Gaussians, so a mixture of Gaussian is within the conjugate exponential family. You can derive the coordinate updating equations. So you can go and use the techniques before lunch. Perfect? Can you use these techniques? Yeah, sure. You can use it as well. Yes. Because at the end, you will have an elbow function, and then you will be able to compute the gradient. The question is like your gradients are going to be Monte Carlo approximations, okay? Are not going to be like the exact closed form, okay? Equation giving you the gradient. So it would be an approximation, and then there is a trade-off. Okay? So here we will see like the elbow doesn't monotonically increase. There is noise. There is the learning rate, it's a bit more tricky. But of course, I mean, specifically using Pyro that implements this kind of black box variational inference algorithm, you can perfectly work with a mixture of Gaussians. Yeah. 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 Let me see. I mean, not really. I mean, not really. Okay? In reality, to make it work, you need a mean field assumption. Okay, perfect. But not really. Okay? Let me see why. So imagine, for example, that you have a neural network, okay? So yes, we are kind of thinking in neural network because they are so popular, but anyway, so let's think in a neural network, okay? So if you don't use it's like, so you have two possibilities. You can use the mean field assumption. In that case, you will have a Q distribution for each parameter of your neural network. So if your neural network has 1 million parameters, then you will have a Gaussian distribution for each of them. And then each Gaussian distribution, okay, will have two variational parameters, the mean and the variance. And then you will have to fit 2 million parameters in order to learn the variational distribution over your 1 million parameters neural network, okay? Can you apply these techniques without the mean field assumption? In principle, yes. You can define Q as a multivariate Gaussian distribution over your 1 million parameters. But the question is like, how many variational parameters you will have to define in order to fit, okay? Or to find the multivariate distribution that better approximate the true posterior. So you have a multivariate Gaussian distribution over 1 million parameters. You will need 1 million parameters defining the mean, okay? Plus the covariance of this 1 million parameters matrix. Not feasible, okay? Perfect. In reality, I mean, people find like, yeah, we need to speed up, yeah. So guys, we need to speed up. So let me see. So yeah, oh my God, yeah. So let's continue, and then let's go to the exercise. Okay, perfect. So what we have done is like, you can go to the same notebook that we have before. Okay, let me see. This one, I need to reconnect, yes. And the idea is like, in this notebook, we are giving you the implementation, okay, of the reparameterization trick. But let me see, the raw implementation, okay? We are computing the gradients manually, and we are doing that for you, okay? And then the idea is like, you just go and play around, and then you observe which is the difference with respect to what you get before with the score gradient. You will see, I mean, these figures with these different gradients, and then you will see really the difference between this guy and this other guy, okay? More specifically, we ask you to play with the number of Monte Carlo samples that we use to estimate the gradient using the reparameterization trick. Perfect? So try with 1, try with 5, try with 10, and see what happens, okay? So the idea was just to, that you get a kind of inspiration what happens when you have like the reparameterization trick, and how in that case, the convergence is much quicker, okay, that when, you are using the score function. I mean, I would say like the main figure is this one, okay? And this is kind of illustrate the different trade-offs that appear here, okay? So what we really want to do is to optimize the elbow, okay? Sorry. To optimize the elbow, to optimize high-dimensional function, because the elbow at the end is a high-dimensional function that depends on the variational parameters we are trying to optimize. Remember, if you have like a neural network with 1 million parameters, then you have 2 million variational parameters to optimize in the case of the mean field assumption. Perfect. If you go farther than that, if you want to go farther than that, you need more parameters to optimize. So it's really a high-dimensional optimization problem. And then you have to compute the gradients properly in order to really optimize this function. So the orange line here is how the elbow function changes when we move across the gradients that has been computed using the reparameterization trick. As we can see, the elbow function increases. We are able to increase it quickly, and then we achieve convergence. The blue line is how the elbow function evolves when we move above the gradients computed using the score function method. In reality, we are improving, but at some point, can you see, we go down. Why? Because the gradient that we are computed, instead of pointing where it's like the true posterior, just point some other direction. Then we don't really increase the elbow, okay? Eventually, we are able to recover, and it's much more noisy, and eventually, in this two-dimensional problem, we are able to converge to a kind of similar solution. But even if we zoom in here, yes, what we can see here is like much more noise. Perfect? As I told you again, when you move to higher dimensional spaces, the score function is not really practical, yeah, in general. So kind of quick recap, okay? It's like the reparametrization trick is a nice thing, but requires this guy to be reparametrizable and these guys to be differentiable. A score function is more general because only requires this guy to be differentiable. There is no really specific requirements about this guy, only to be computable. It's much more general, but has the problem of, being more general, but it's more not applicable, especially in high-dimensional space. Perfect? So let me see, of course, when your probabilistic model falls within the conjugate exponential family, when we can derive these updating equations manually, is also a nice alternative. Even though we can apply some of these techniques, okay, it's better to have, if possible, the updating variational equations because you don't have the noise in the gradients, you just are kind of directly optimizing monotonically your elbow function. So in that sense, the automatic variational inference, and this is something that appears in probabilistic programming models, so you start always defining your data model and your prior, okay, which is not easy, perfect, but this is how you should proceed. You define your variational distribution family, usually manual, but there's also the possibility to do it automatically using default variational approximation. Like when you have a continuous parameter, then you use a Gaussian distribution. Then we can optimize the elbow, and then the elbow is something that is optimized automatically, okay? Why is automatically optimized? Because we can compute the gradient, okay, of the elbow function using one of these techniques. And if we need to compute some gradients, okay, as we see before when you are using the score function or representation trick, we can have these automatic differentiation engines that give you the optimization of the elbow. So at the end, also using one of these optimization packages that are usually integrated in any of these deep learning libraries. So what we have is a complete automatic, almost automatic recipe in order to do variational inference over very general probabilistic models. Where our main focus here is to define the probabilistic models, which is where all the effort should be put, which is we use our expert knowledge, we use, and then we define a probabilistic model that is going to solve the kind of problem we aim to solve. Perfect? So, any questions so far? Yeah?
So it seems like the major limitation.
Sorry, say again?
It seems like the major limitation of the score-based method is coming from the Monte Carlo or the samples that you're taking. If you can do something there to improve the samples, or has there been any work which is kind of between the two extremes?
Yes, that's a good point. Yes, the main limitation of the score function is the Monte Carlo sampling generates has a lot of variance, okay? And then it's people has gone to the Monte Carlo literature and has applied a variance reduction method, okay? That reduces the variance of the Monte Carlo estimation, and that helps a lot, okay? But in practical settings, if you can use reparametrization trick, this is the way to go, okay? Because you are exploiting the gradients, okay? You're exploiting the gradients of the model when you're computing the gradient of the elbow. And that contains a lot of information, okay?
Yeah, it is limited by what all you can do.
Exactly. It's limited because, you need to be reparametrizable, but this is not being a real limitation. So there are a wide range of densities where it can be reparametrized, okay? And then it has to be differentiable, the log likelihood of the model. So it imposes limitations in the context of having models where you don't have even the density, or having models that involve discrete variables, okay? But there are also tricks to this within the reparametrization trick, okay? So we are just telling you the basic ideas, but there are a lot of works in that direction, but mostly people rely on the reparametrization trick. Yeah. I would say that that's the way to go solution. Yeah. And it's the default option that is implemented in these probabilistic programming languages. Yeah. Any other questions so far?
Otherwise, we are going to continue with the variational setup. So Andrés and Helge took you through all the mathematical detail in coming up with different variations of estimating the gradient of the elbow with a score function and the reparameterization trick. Now we're going to see how that actually is implemented in Pyro, or rather how we can use these techniques in Pyro. So both the score function trick and the score function and the reparameterization trick are both implemented in Pyro. So you can actually use both when you're doing inference. So I think we have already covered Pyro quite a bit yesterday. There we mostly focused on the modeling part that we have up here. And now, so as I mentioned, we are going to look at the inference part. And again, emphasizing that Pyro here is just one of the existing tools in the wide range of toolboxes available out there. So many of the things that we are talking about now and underlying concepts would also be applicable if you move to one of these languages. So just a brief recap from yesterday. So we had a simple running example where we specified in Pyro, again from a purely modeling perspective. So we were modeling the measurement of a temperature. We had a variable temp that was sort of the true temperature in a room, say, and then we had a sensor measurement that followed both the first temperature variable followed a normal distribution with a given mean and variance. The sensor variable is a sort of a noisy represents a noisy observation of the temperature with a mean corresponding to the actual temperature and then with a noise term corresponding to a variance of 1. And collectively, this model that we have up here defines a joint distribution over these two. In moving this model into Pyro, we have the Pyro sample statement that allows us to define random variables. And if we also augment that with the observation argument or the observation keyword, then that corresponds to observed random variables. So taking this and implementing that in Pyro, we have this piece of code down here. Again, the observations in the dictionary here correspond to our data. Then we define our model. We have our first variable temp defined by the sample statement, given a prior distribution out here, and the sensor defining the sensor variable, again with a distribution, a likelihood or a normal distribution here with a mean corresponding to the actual temperature, and the keyword out here indicating that that's observed based on the data that is being provided up here. So that was what we covered yesterday. Now, when we want to do inference, this is where we are going to use the variational machinery. So in the particular case here, we have a very simple inference problem where we are looking for calculating the posterior distribution over the temperature, given that we observe the sensor variable to have the value 18. So in terms of our variational setup, that corresponds to minimizing the KL divergence between a variational distribution over the temperature variable and then the posterior distribution over the true posterior distribution over the temperature variable, given the sensor observation here. So for specifying our variational distributions, we use so-called guides that is defined in Pyro. So the way that we define our guides is the way that we define our variational distributions. And as a side note, these distributions here, these guides that we have defined in Pyro, can also be used to drive some of the other machinery implemented in Pyro, like importance sampling and MCMC. But we will only focus on the variational part. So just as models in Pyro could be arbitrary stochastic functions, the same holds with guides. So they are just arbitrary functions that covers the variables in the models that are not observed. So that's basically a guide should include variables that matches the variables in the models that do not have the observation statement, the observed statement. So that's one of the requirements that we have. The other requirement for designing a guide is that the signature of the function should be the same. So if the model has certain input parameters, then the guide should have the same, and similar for if there are any return statements, not often the case, but if that were the case, then it should also be the same thing there. So here's an example of the way that we define a guide for our model here in Pyro. So this is the model from before. Now, temp is our unobserved variable that we would like to calculate or approximate the posterior distribution over. In order to do that, we define a variable down here having the same name, so temp here matches the temp that we have up here, and they should match identically in terms of names. And then it's given the variational distribution, our approximating class of distributions, is now a normal distribution that has two variational parameters, A and B. And these variational parameters are defined up here with the pyro parameter statement. So we have A corresponding to the mean, and that's initialized with the value of 0. And we have the scale that is also defined in a pyro parameter statement, initialized to 1. And then we have the constraint out here that this value here should be positive, since it corresponds to the standard deviation. So that's quite important just to be aware of, that there are certain parameters here that you need to enforce to be non-negative. And this is the way that Pyro uses that. So now we wanted to do an exercise, but for the sake of time, we'll just go directly to the solution. This here is just a very simple example, and we'll take a slightly more elaborate example later on. So you may recall that before lunch we did the coordinate ascent variational inference on a simple model where we had an unobserved mean and unobserved precision gamma, and then we had a bunch of observations xi, 1 up to n, and they all followed, were observed. These observations corresponded to realization of a random variable that followed a normal distribution with a corresponding mean and precision. And what we want to do now is to solve the same problem here, but now using Pyro and specifying guides. So we have the same setup as before lunch. So we here generate 100 data points. This is what we have here. We generated from a normal distribution with a mean of 5 and a precision of 1. So these numbers are nice just to keep in the back of your mind for later reference. So this is our specification of the data. Then maybe I can have everything here. Let's see if I now close this one here. Yeah, I think we more or less have the model and the graphical illustration on the same. So here we again have the model up here. We have implemented it down here in Pyro. So not much new. We have gamma matches gamma up here. Initialize, it follows a gamma distribution with parameters 1 and 1. Mu follows a normal distribution with a mean of 0 and a very large standard deviation. And then we have our plate construct. This is again for vectorizing the calculations, where we have each of the x's, our data points, comes from, or the random variables for our data points, follows a normal distribution with the specified mean and standard deviation. And again, using the observed statement here to indicate that this is observed. So we can run this. And now we have here our guide specification for our variational distribution. Yeah? Here I would expect that it's simply that Pyro underneath simply monitors sort of where the step size and then clips the gradients. But maybe you know. Yes, but how it's done internally within Pyro. I would guess that it has something to do with monitoring sort of the ranges of the parameter values and then adjusting according, maybe a bit along the same lines as Helge had for controlling the steps in the previous notebook.
Yes.
But
I think like internally we also use this kind of soft max, soft plus transformation as well. Not
could be, I'm not. But this is now the guide specification that we have. So we have two variables that are unobserved, our mean and our precision, mu and gamma. So we define them down here, mu and gamma. And again, notice the clash of names. Starting with gamma up here, we have specified a prior distribution, or the prior of gamma as a variable follows a gamma distribution. We follow the same convention in the posterior distribution. So we define that as a gamma distribution with alpha q and beta q parameters that are given up here, initialized to 1, and given the constraint that that should be positive. Here we specify our normal distribution for the mu, so the posterior distribution follows a normal with a given mean and standard deviations defined as pyro parameters, so variational parameters to be optimized, and the scale also has this positivity constraint implemented. We have that, and then we can start to do the learning. And this here is sort of the learning setup, the loop, sort of where we do our stochastic gradient descent. Here we're using a fancy Adam optimizer for controlling the learning rate, not important. Here Pyro is clearing the parameter store, so basically initializing the variational parameters. We defined our stochastic variational inference objective, where we have the model, the guide, the optimizer, and then our loss function, or the function to be optimized, the elbow. And then we are simply looping here for 3,000 epochs. Here we are taking a variational step, or a gradient step, with svi.step with respect to our data, calculating a loss, which is sort of the negative. We are trying to maximize the elbow corresponding to minimizing our loss. So we are minimizing the loss and then maximizing corresponding to maximizing the elbow. So the loss here is the same as the elbow, but using the terminology of loss because it uses the underlying PyTorch machinery where you're doing a gradient-based optimization of a loss function. So it's just borrowing the concept from that. And then we are sort of tracing the individual steps. So if you run this, it takes a bit of time. So while we wait, maybe point out here that you can see that we don't have, as not unexpected, but we don't have sort of a steady decrease. So we are here reporting the loss, by the way. That would be the negative of the elbow. So here we wanted to go down, but you can think of it sort of as maximizing the elbow. And we see here that we can both have decreases and increases in the loss, but it's sort of generally going in the right direction. And this stochasticity is because that we are doing stochastic variational inference in the sense that we are using the reparameterization trick for moving in the space of our variational parameters. Here are the learned parameters that we have. So alpha q and beta q would be the variational parameters for our gamma distribution. We had an initial precision of 1. So here it should also be mentioned we haven't converged yet. If you divide these two guys here, you would get the expectation. So it's not too far from 1. And here we have the mean and the standard deviation associated with mu. And we started out with the correct mean of being 5, and we see that we get pretty close to that also. And here we have sort of an illustration of the evolution of the elbow. And again, you see that there's a steady increase, but we also see some spikes where we are dropping. Again, this is because that we are using the reparameterization trick to calculate our gradients. But the main point here is mostly that the use of guides by Pyro to specify the variational distributions. A few questions? Yeah?
What's the importance of how you initiate the values of the parameters in the guides? Should you initiate them as the prior values or not necessarily? Because you define your prior in your model, but you still have the same parameters like the alpha and the beta in your guide. Should you best also specify those parameters as your prior parameters, or what is the importance of defining that alpha q is 1 and beta q is 1?
So it's not necessarily something that has to do with the prior. So you need to initialize your parameters in one way or another. It would probably be a good idea to simply use the prior specification as your starting point and initializing your variational distribution the same way. But it's not a requirement, so it's just you need to assign some values for initialization. And obviously, the closer you are to what you expect to be corresponding to the variational posterior parameters, the better it would be. Yeah?
Is it possible to do custom loss functions?
Yes, you can also define your own loss functions, but that would require, it's a bit outside what we are going to make today. Yes. Yeah?
Which parameters are optimized? So only the parameters I define in the guide, or if my model takes another parameters, does it also, or how does Adam get the parameters?
So that's a good point. We'll also see it a bit later in the evening, but here we can actually do all the parameters that are, all values that are defined as parameters will be optimized. So if you also have parameters in your model specification, they will be optimized along with the variational parameters in your guide specification. So that was actually something that we used yesterday when we were calculating maximum likelihood estimates for our temperature model. We dabbled a bit around in that. And that's the same setup, so where you have these parameter specifications. Other questions? Yeah? Sorry?
To fix a seed for the procedure.
Yeah.
Be reproducible.
How? You don't need to do it. I can't recall whether we did it here, but if so, that was just for. Yeah, we did. We fixed the seed here, but that was just to make it reproducible again.
Yeah, but my question was that the seed here is needed only for the creation of the data set so that we have all the data, or is a step needed by the procedure?
It's also needed during the variational inference because you're also sampling from your variational distribution or you're also sampling when you're calculating your gradients. And depending on whether you're doing score function or reparameterization trick, you would be sampling from different distributions. But yes, that also comes into play.
And it uses NumPy as seed, not torches?
This here would actually only affect the data generation. You're right. So it would be a torch. You would have, yes, you would have to define your own seed and torch. Good point. Yeah. Yeah, so it would just be random, yes. Yes. Good. So let me just move on. So this here was sort of how we can define guides. And just to show you sort of a slightly more elaborate example, we can return to our favorite model class, our Bayesian linear regression models. We will at some point later see a slightly more complex model, I promise, but for now we'll stick to this one. So we have our RocketNest data set from before, linking the RocketNest of a country with its log GDP and separating it from African and non-African countries. And again, this here is our data. And we have defined that within a data frame for African and non-African countries. Oh, sorry, not a data frame, a Python dictionary. Sorry. A bit of auxiliary code for illustration. So again, this is what you've seen before. Linear regression, I'm just going to show you as, again, a reference, but again, this code here is actually a complete copy from the code that you saw earlier. So I'm just going to go relatively quickly through that. So we have our model specification here using PyTorch. We define our model. We do training, define our training function. We do the training. We have one model for non-African and African countries, so we come out with two model classes. Here are the corresponding weights for non-African and African countries with a bias term and a slope, again pointing in where the slope shows a different correlation whether we are talking about African or non-African countries. We can do evaluation of our model. And we see the trend line here and get some information about the values. But now the more interesting part is our Bayesian linear regression. And here we again have defined it in a slightly more general terms that we actually need. We are still separating out the bias and the weight, but the weight vector over here is actually just a scalar. So that is the weight of the ruggedness index. And here we have the bias, again, a scalar. But in contrast to what we saw earlier, we are also explicitly modeling the theta, the precision, as a random variable. So now we also want to estimate this variable. And theta is a priori given a gamma distribution with parameters 1 and 1. But otherwise, the model is identical to the model that we explored previously. And again, it defines collectively a joint distribution over all our unobserved variables theta, b, and w. Here we have the Pyro model specification. And I'm using here S for the slope. We have the bias term b, initialized according to given a prior normal distribution. We have a rather wide standard deviation for the bias, indicating that we are quite uncertain about that. We have our variable theta, given a gamma distribution. Then we make the combination of the bias term together with the data and the slope, and use the Pyro deterministic function for defining that combination. And that is because we want to later on extract the value of this combination, and we call that the predictive mean. And the predictive mean is then defined as the mean of a normal distribution for our y variable that is observed according to the data that we provide for our model specification. And we can still use the rendering functionality from Pyro, and with this here is the model that we have. The deterministic function is put out here because it's just a deterministic function, the predictive mean. Then returning to the guides. If you're very lazy, then Pyro actually provides you with some functionality for automatic guide generation. So maybe you just want to have something up quick and dirty up and running and don't want to bother with the guide specification. In that case, you can use the auto guide library where Pyro has some different guides that are automatically being instantiated based on your model specification that you can then use. There are several of those. If you're less lazy, you can define your own guide, and this is what we've done here, our customized guide. And here we have our, if we take the bias term and the slope, so they are both given, we are here defining our variational distributions. They are assumed to be normal with a given mean and standard deviation. And the mean here is defined as a Pyro parameter, and same as the standard deviation. And there we prefix them with Q underscore to indicate that they are part of our variational distribution, so a location and scale. Again, we use the constraint on the scale to ensure that it's always positive. For our theta, that's the precision of our model, that's assumed to be a gamma distribution with values or parameters Q theta alpha, Q theta beta, that is again defined as Pyro parameters, both of them being positive. Yes?
So if we use the delta distribution as the guide, as the variation approximation, we always obtain the maximal superiority.
If you use the delta, then you could get a map estimate, yes. If there's a derivation for that? There you would have to look into the Pyro documentation and see how it is. Yes.
I don't see directly how we can go from like maximizing the elbow to like getting maximal posterior. I mean, I think it's connected.
Yeah, I'm not sure how it's actually being calculated, but I think let's take it afterwards, and then we'll take it in the break when in 15, 20 minutes. Because, yeah.
The question of like, with that the functions, because you have like nice differentiability, right?
Yeah, so here I would expect that it's being approximated, but I cannot, from the top of my head, give you the details of it. But we can try to look it into in the break. But I'm afraid that we'll have to continue here. Yes. So here we had our customized guide, and then we can do inference. And the setup here a bit longer, but it's more or less the same. So we have provided functionality here where you define, it takes the data, the predictor variables, the response, the model, also a guide. If you don't specify a guide or provide a guide, then it assumes an auto-normal guide. So that's the one of those that are provided you by Pyro. We have our stochastic variational inference based on where we're optimizing our elbow. And we are using, in this case here, 10 samples for the optimization. Usually it will probably just be one. That's the default value. And then we are simply iterating here. And we are doing this twice. So the outer loop that we have here is just iterating over for African and non-African countries. And let's do the training and see what we get. Again, now we have sort of a steady decrease in the loss corresponding to maximizing the elbow. This here was not an increase in itself. It's simply because that we are running two models here, and the second model starts here. We print out the parameters, and these are the parameter values that we find. And maybe you can sort of recognize sort of some of the values from previously. If not, then we can visualize it instead. And do model evaluation. So this here is then the result. So this is the predictive mean. You remember the deterministic function that I defined earlier, the values that we see here and here for the two parts of the data set. We can also take into account the uncertainty that we have in the weights, in the weights that correspond to the slope and the bias. And for that, we previously did this calculation ourselves. That was when we sort of were working with the Kavi model, or the Kavi notebook. Here we can actually use I have that up here, the predictive functionality, posterior predictive functionality provided by Pyro. So this is embedded in this Pyro Infer predictive model specification that we have up here, where we are generating samples from our posterior predictive distributions, and there we can access, in this case here, both the predictive mean and also the standard deviation of the samples when we sample from the weights of our model. If we also want to take into account the uncertainty that we have in our response variable, then we get uncertainty bounds, 95% credibility bounds, looking like this. And again, here it looks a bit more rugged, but if you recall the same kind of uncertainty plots that we had, or credibility plots that we had previously before lunch, then you can see that sort of has the same shape. And lastly, we can also start to look at the uncertainty estimates for instance, for the slope. Good. Yes?
The plots underneath this are way more jagged.
That you see here? Yeah. This is simply because that we are sampling. So all this is these plots here, based on the functionality provided by Pyro, is based on sampling techniques. So we are sampling from our posterior in order to get the posterior predictive distribution. And previously, we calculated exactly and showed the predictive distribution there. That was why it was much more smooth. Other questions? Yes?
Usually the uncertainty estimates, like this shaded region that we have, is narrower when there are more data points as compared to like when there are like very sparse data points.
Mm-hmm.
Here they kind of go as a wide band. Why is that? Is there a reason or?
So this year is also because that we have a rather large amount of uncertainty associated with our response variable. So that's why we have this wide band. If we disregard that part and only focus on the uncertainty that follows from our posterior distribution, then we would, for our bias and the intercept, then we would have these bands here that are more narrow. Other questions? Okay, so then we are close to, yes, close to the next exercise. So here we will be using the same data set again for you, but now with a small twist. So we have the data set loaded here, so everything is as you've seen before, but now rather than dividing up the data between African and non-African countries, what we want to do now is to predict where a country is located based on the terrain ruggedness and the log GDP of that country. And then we are defining a logistic regression model. So here we have our data. We can illustrate plot the figure or plot the data. And this is what we get. So we have the ruggedness index on the x-axis, on the y-axis log GDP, and then the color coding corresponds to whether it's an African or non-African country. Here we have a logistic regression model, completely standard, nothing Bayesian about it, and we can define that using PyTorch. We instantiate our model, do a bit of training here. And now we evaluate it. And this is sort of the decision boundary that we now find with our logistic regression model that sort of tries to separate out the yellow and the green dots. Now we want to put this into a Bayesian framework. So we define a Bayesian logistic regression model where we are sort of the graphical specification is similar to what you've seen before, but the underlying variables are different. So here our y variables now follows a Bernoulli distribution, where the logits here are given as a linear combination of the weights of our model and the input. Now our input is both the log GDP and the ruggedness index, and we also have a bias term. And then we put normal prior distributions over the weights and the bias. But again, remember here that this here is 2 parameters rather than 1 that we had before. And then we have our combined probability model here. We have a model specification below. And what you should do now is to come up with your own guide specification. You should define your own model and then use the orthonormal guide for estimating the variational posterior distribution of the parameters of our model. So your task here is to define the random variable for modeling the intercept and another variable for modeling the response variable following a Bernoulli distribution here. You can use the auto guide. If you want, you can also define your own customized guide. But this here would be fine. And then we have some code underneath that allows you for setting up the training and outputting the parameters and exploring the model, the underlying model uncertainty. So that's the setup.